Okay. So let's see what we have. We've got a simple supported beam, 10 at A, a roller at B, and a little bit off center here we have a point load. And we need to determine the slope and displacement at the midpoint of the beam. How can we do that? Can we do direct integration on this? We can. It'd be a little bit tedious because we'd have to develop a set of equations that are good from 0 to 9, and then a second set from 9 to 12, and then we would generate, 4 integration constants and have to solve those 4 equations simultaneously. But once we did it, we would have it. And then I could simply just take my first equation and plug in at x equals 6 and calculate displacement and slope. All right? And on top of that, I'd have an equation for displacement and slope everywhere in the structure. So that is possible, but a lot of work. Our second approach that we've talked about so far would be conjugate beam. And since it only wants the slope and displacement at a particular point, the center, conjugate beam would also be possible and probably a little more straightforward to do. So that's the approach we'll take here. So what do I need to do for conjugate beam? What's step 1? I have to draw the shear force and bending moment diagram, right? So I'm going to start by doing that. So let's assume that we have a positive shear at A and positive shear at B. And I want to find those two values. So how do you want to do that? Yeah, probably take the moment someplace, A or B. Which one would you like? Pick one, Mr. Wynn. A. So we'll sum moments at A, and I will assume right-hand rule for my sign convention. So we'll sum moments at A. Make sure it's in equilibrium. So summing moments about A, my applied 5 kip force creates what kind of moment about A? Positive or negative? Negative. So that's 5 kips times 9 feet. And then the moment at B, the shear at B, that's positive shear at B, also creates negative moment. And it has a moment arm of 12. So what is the shear at B? What is that? That looks like 45 divided by 12. What's that? I need a calculator. Somebody with a calculator help me out.
3.75.
3.75? And that would be negative. So the shear at B is negative 3.75. And then if we sum forces in the y direction, and I'll assume up is positive, and make sure we have equilibrium, what do we have? Well, we've got the shear force at A acting up, the shear force at B acting down, and then the 5 kip force also acting down. So I can find my shear at A, and that should be 1.25. Okay? Not too bad. So let's draw a quick template of the structure. So there's my left and right side. I'll go ahead and identify positive x-axis, positive shear, and we'll let all these have units of kips. So what is the shear at A? 1.25. And we know from our previous work that the change in shear is the area of the load diagram. And you see, first 9 feet, there is no area of the load diagram, so there's no change in shear. So I should have added this line here at 5, where the 5 kip force is. So I have no change in shear. And then as I go from the left side to the right side, you can see my change in shear is equal to the load. That's minus 5. So 1.25 minus 5 is negative 3.75. And we get our shear diagram. And again, no change in shear. There's no change in shear because there's no load. So now I can estimate what my moment diagram looks like. Again, positive x, positive moment, and all these will have units of kip feet. So what is the moment at A? It's a pin, so it's 0. What's the moment at B? Also 0. So I know the change in the moment over the first 9 feet is the area under the shear diagram, which is what? 1.25 times 9. That's a positive area. What's that value?
11.25.
11.25. And the shear is constant, positive, so we have a constant positive slope. And then the change in shear of the last 3 feet should be the area to this part of the curve. So this was a positive area. This is a negative area. So that's 3 times 3.75. Hopefully that's negative 11.25. And that brings us back to 0. And the shape of the curve is given by the slope. The slope is constant and negative. So here's a constant negative slope. So there's my moment diagram. Easy enough? So now what do we do? Well, in conjugate beam, we take the moment diagram and we apply it to the conjugate beam. So what does my conjugate beam look like? So going back to the geometry, a real pin connection at the edge is what in the beam? A pin in the conjugate beam. A real roller is what in the conjugate beam? A roller. So my diagram looks pretty much the same. So I've got a beam 12 feet long with a pin and a roller. So that's my geometry. And then I apply as load my moment diagram divided by EI. So I'm going to come over here and apply my moment diagram. It's the same shape. Now this is positive moment. What direction is positive load? Up or down? Up. So this is actually a load that's up on the beam. And the maximum value here is 11.25 kip feet. That's the moment. And then we're going to divide it by EI. And remember, the dimensions are the same. This will be 9 feet, and this will be 3 feet. So now that you can completely ignore everything now and just work this problem. If I gave you this problem, a simply supported beam with this kind of triangular distributed load, and ask you what's the shear and moment in this beam in the middle. So I would imagine that you would do something like this. You would come kind of right here in the middle and draw your line. There's the midpoint. And you're asking yourself, do I want to work the left side or the right side? Yeah, I think there's a clear choice here. The left side is simply just a triangular load. The right side is a trapezoid and a triangle. Little more to do. So let's do the left side. And if I do the left side, I probably need the reaction over here at A. So I'm going to come back over here and assume that I have a positive shear at A. I'll go ahead and write my positive shear at B, but I'm not really interested in computing that right now. So what's the easiest way to find my shear at A? Sum of B. Now to make it a little easier for you to see this, I'm going to redraw the beam. And just put on it the concentrated equivalent forces. So looking at this triangular load right here, right, I'll call that force F1. We'll compute it in a second. And what's the distance from A to the centroid of this triangular area, this part right here? It'd be 2/3 of 9, right? So that would be 6 feet to there. Now this little section here that's green, I'll call that force F2. What's the distance from B to that force? Also 2/3 the distance, and 2/3 of 3 is 2. So once I know that, and I know this beam is a total of 12, so this is 6, and then this would be what? What's the difference here in the middle? 4. Everybody see that? So let's actually compute F1. Well, F1 is this area under the triangle, so it's going to be 1/2 base, which is 9 feet, times the height, which is 11.25 kip feet, divided by EI. What's that going to be equal to? Somebody compute that for me. And while you're doing that, we can compute F2 against a triangle. 1/2. The base of that one is 3, and the height of that one is 11.25 kip feet divided by EI.
Do you want it in terms of EI?
I'm sorry, say that again?
Do you still want it in terms of EI?
Yeah, just give me the number. What's 11.25 times 9 divided by 2? I'm guessing it's 56.25. I'm just guessing.
50.625.
Oh, 50.625. 50.625. And that's kip feet squared. Sorry, my number got kind of mashed up here at the end. So what's F2?
16.875.
What'd you say?
16.
16.875? Anybody else getting that?
Yeah.
Yep. So that's 16.875. That's kip feet squared over EI. All right. So I've got those values, and I know that I have my sheared A and my sheared B. And what do we want to do? We're all back to finding that. So let's come over here and sum moments about B. Make sure this conjugate beam's in equilibrium. So both these forces, F1 and F2 about B, create what kind of moment? Positive or negative?
Negative.
Negative. So I'm going to have minus F1, which is 50.625 kip feet squared divided by EI. That's the force. What's the distance from B to that? Looks like it's 6 feet. Then F2, which is 16.875 kip feet squared divided by EI. That's F2. And the distance to its centroid from B looks like 2 feet. Then all the way over here, I've got my reaction at, my shear at A, which is also negative. And it has a moment arm of 12 feet. So I should be able to solve for my shear at A. It looks like it's going to be negative. You guys have to help me out with that. $28.75, I'm guessing. Nobody? You'll have to make 28.125. And that will be kip feet squared over EI. I don't really need that value, but I need it to get to where I want to go, which is when I'm going to cut the structure here in the middle, look at the internal shear force and bending moment, I'm going to need that. So let's now go back and draw this free body diagram we had talked about before. So in this particular case, that'll be right in the middle of the beam, so this will be 6 feet. We just computed the in reaction force. I assumed it was up. I got a negative, so this is going to be 28.125 kip feet squared divided by EI. That's acting down. And then I've got my load, which is triangular shaped, and it's acting up. First thing we have to figure out is what's the intensity of this load. Well, we know it's 11.25 over EI here, and that's at 9 feet. So at 6 feet, it should be, what, 2/3 of that? What's 2/3 of that? I think it's 7.5, isn't it? I'm even wrong about that. I'm maybe getting...
It is 7.
Is it 7.5? So that'll be 7.5 kip feet divided by EI. And then, of course, there's the shear, positive shear, and there's the positive bending moment. So to make things easier, I'm going to, again, convert this to a concentrated equivalent. I'll just call that F3. And from the cut to the centroid is what? 1/3 the distance? And 1/3 of 6 is 2 feet. So what's F3 going to be? What's a triangle? So it's going to be 1/2 the base, which is 6 feet, times the height, which is 7.5 kip feet, divided by EI. What's that equal to? 22.5? So 22.5, and that will be kip feet squared over EI. So now what I'm left to do is to find the shear and moment. So I'll start with the moment first. So we will sum moments at the cut. That's here. So we'll start with the internal moment. In my sign convention, that's a positive moment. The moment about the cut due to F3 is positive or negative? Negative. So F3 is 22.5 kip feet squared divided by EI. That's the force. And what was the moment arm? 2 feet. And then I've got the reaction force way down here in the bottom corner. That's going to create positive moment. And that one is 28.125 kip feet squared. And that distance is what? 6. So what is the moment? It looks like it's going to be positive. No? No, it's going to be negative.
Got 123.75.
123.75?
That's what I read. Or negative 123.
123.75, and that's going to be kip feet cubed over EI.
Dr. Jim,
Yeah.
how does that kip feet squared and feet cubed cancel out? Is it from the EI? Will that make
Yeah, the EI will take care of it in a second.
Okay.
So we can do it right now. So let's see if I can squeeze that in here. So remember that moment translates to displacement back in the real beam, right? So that will give us a value of minus 123.75 8.75 kip feet cubed. So now let's divide by EI. In this particular problem, E is 30,000 kips per inch squared. I is 800 inches to the fourth. And then we got to convert this cubic feet to cubic inches. So that would be 17,028 cubic inches in a cubic foot. So if you look at that, you can see the kips cancel, cubic feet cancel. So the numerator has inches to the fifth, the denominator has inches to the fourth. That's a unit of inches.
That's an interesting way to convert things.
So what do we do with that? We compute it. So punch that into your calculator. I think I can just squeeze it in here. I believe it's going to be a number less than 1. Anybody get it? 0.0089. That seems too small.
00891.
0.00? 89. I'll just say that. That's pretty small, isn't it? 9 thousandths of an inch. That's pretty small. But then again, let's think about it. I got a steel beam, only 12 feet long. That's pretty short, really. And I've only got a 5,000-pound load on it, and a beam with a moment of inertia of 800. That's relatively large. So this is a pretty stout, short beam with not much load on it. I left myself very little room to complete the problem, so I'll have to slap on another page here.
So the moment at that point is going to be equivalent to the displacement at that point.
Say it again.
The moment at that
The
point.
moment in the conjugate beam is the displacement in the real beam. So now, what's the shear in the conjugate beam going to be? The slope. So let's look at what the shear would be. So I'll try to squeeze this in right here. So we'll say if we sum forces in the y direction for our free body, all right, what do we have? Well, the shear force is down. My F3 force is up, and F3 was this 22.5 kip feet squared. Oops, my line got out of whack. Sorry, over EI. And then what else do I have? I've got this force acting down, minus 28.125 kip feet squared divided by EI. So what is the shear? Looks like it's a really small negative value.
Negative 5.625.
Negative 5.625. And that's kip feet squared over EI. That's really the slope in the real beam, right? So what's that equal to? So we'll do the same thing. So I've got 5.625 kip feet squared, and now let's divide it by E and I. So first we'll divide it by E, just like we did before. That's 30,000 kips per inch squared. And then I was 800 inches to the fourth. And now I've got feet squared, right? So how many inches, square inches and square feet? It'd be 12 squared. So that's 144 inches squared in a foot squared. Now in this case, kips and kips cancel. Feet squared and feet squared cancel. I got inches to the fourth in the numerator, inches to the fourth in denominator. So I had a dimensionless number, which is a good which is a good value for slope. It's probably going to be really, really small, and it's going to be negative. Anybody calculate that?
When you say really small, is it like 0.0000?
I think so. How many zeros?
4.
4 zeros? After the decimal point?
The decimal.
Wow. 1, 2, 3, 4, and then a number?
3375.
337. Let's just say 3, 4. And that will be in radians. That's a pretty small angle. So we got a negative displacement and a negative slope. Let's go back and look at our original problem and see if that makes sense to us. In the center point, I would imagine that this would go up or down? Down. So that makes sense, negative displacement. Would the slope here be negative or positive or 0? Well, if it's negative, probably this whole section is negative. At some point, it will find a 0 slope and then start back positive. So that seems reasonable. I don't think the maximum displacement is occurring at the center when the load is shifted to the right. So the maximum displacement is probably shifted to the right. You can see, as our calculations showed, it's a pretty small angle. We're getting pretty close to 0, but we're not there yet. And we're still negative, so we're still heading down.
Where are the forces going up when they conjugate beam?
Because the load, the load is the moment, and the moment is positive, right? So when you positive load is up. When you apply the moment divided by EI as load on the conjugate beam, it's a positive load. So positive load is up. If you had a negative moment, then it would be down.
So on this one, it happens to be like the entire moment was positive. What if like that second triangle after the 5 kips was negative? Then what would you have done?
Then you'd have a section with a negative load.
You would have still done like F1 is up, but then F2 is down, and you would just still do that. Okay.
Be a little more challenging, but not much more. So really, all this turns out to be is a combination of your skills from the first part of the course. Drawing a shear moment diagram. And this is not a relatively difficult one. And then applying that for load. And at this point, hey, just find the internal moment at a point. But on the first exam, what used to be 2 problems is now 1. So like I advised you earlier in the course, if you were weak in shear moment diagrams or weak in finding internal forces, we're not going to stop doing that for quite a while. Probably till the feast.
When is the second exam?
It's the Thursday before the Tuesday feast.
The Thursday?
Yeah. Which would be November 30th. The last day in November.
So it would make that Tuesday of the next week final?
Yeah. No, the Tuesday of the next week is the last day of class where we test your bridge, I return the second exam, and we feast. Then the following Tuesday...
Oh, the feast is for the bridge. That's right.
Yeah.
Okay.
And the following Tuesday, December 12th, is the final.
Gotcha.
And that's December 12th